All right, pre-cal, this is section 4.4, graphing sine and cosine functions. So yesterday we took some time to take the information that was on our unit circle, our plate, and we took that information and we plotted it on a coordinate plane so that we could find out what the general shape was of a sine graph, cosine graph, and a tangent. What we're going to do today is we're going to dig deeper into sine and cosine because those functions look very similar to each other. We're going to look specifically at those two sine and cosine waves and see how us adding, subtracting, multiplying, dividing different numbers within the cosine and sine functions will change or transform the shape of the graph. Okay, so we're going to start with the cosine function, and we're just going to kind of do a general sketch to start with. Since we went over it in detail yesterday, we're going to do a basic sketch to start with, and then I'm going to talk about the details within these two functions that can transform our sine and cosine functions. Okay, so the first thing I want you to do is add an x and a y axis to your graph. So our x-axis in this case represents theta, and our y-axis represents the cosine of theta. So all I've done is go in about 2 squares for my y-axis, and then for my x-axis, I just kind of cut that in the middle. So from our unit circle, we know that theta, or our angles, we are starting at 0 radians, and we went all the way around the circle, which was 2 pi radians. So I'm going to go every 2 spaces and mark this off on the x-axis, and on my 4th mark, I'm going to label that as 2 pi. We're not going to be plotting all of the same points that we did yesterday. Yesterday was detailed. We used all of the angles around the unit circle. Today we're just going to look at a few specific angles. So my last mark on the x-axis is 2 pi, and I'm going to cut this up into 4 even spaces. So halfway is going to be pi. 1/4 of the way, or the first mark, is going to be pi over 2. And then halfway between pi and 2 pi is 3 pi over 2. So I've just divided my graph up into 4 spaces on the x-axis. We could have done every 3 marks on the x-axis. You could spread it out as much as you want to. I was just trying to give us a little bit of space here. And if you notice looking at your graph from yesterday, the sine and cosine functions from the unit circle, the highest they go is 1, and then the lowest is -1. So again, I just went 2 spaces up and down from the x-axis and labeled 1 and -1. So the cosine function that we're graphing first, if you remember the patterns that we saw, it was very similar to sine, but it started at +1. At cosine of 0 is +1. And then we're going to skip some angles. We went straight up to pi over 2. The cosine of pi over 2 is 0. Cosine of pi is -1. 3 pi over 2 was at 0. And back around 2 pi is +1. So if I just connected these 5 points, it would look like a V, an absolute value function. We know that's not what it looks like. I'm skipping some angles here just so we can look at these 5 main points, but we're going to connect the dots with a curve because we know what this graph should look like. So when you connect your dots, we're going to kind of curve in between those points. Remember, it's easier if you go a quarter at a time and draw your quarter of a circle. And then we know that this graph continues infinitely in both directions. So here's the basic shape of the cosine function using those 5 key points. Okay, I'm going to do the same thing for the sine function. So I've labeled my x and y axis again. Remember, our x-axis is our angle theta. Our y-axis this time is going to represent the sine of theta. I'm going to use those same key points. So I'm going to go every 2 spaces. The last one is 2 pi, and then we're just dividing that up into 4 equal spaces. Again, the sine values, highest sine value is 1, and the lowest sine value is -1. So remember, sine and cosine were technically the same function. It was just shifted over. So the sine function started at 0, 0. The sine of 0 was 0. And then pi over 2, it was equal to 1. At pi, sine was equal to 0. At 3 pi over 2, sine is equal to negative 1. And then at 2 pi, it was back to 0. So we've got our basic shape for our sine function. So we know what it looks like. It continues infinitely in both directions. Okay, so remember, sine and cosine are technically the same graph. One is just a shift or a translation of the other. Notice the equations that we have down below. Yesterday, we just graphed sine x and cosine x. That was just the basic parent function. Today, we're going to see how all these different numbers, a, b, and c, can transform the sine and cosine functions. So let's talk about all these different things within this equation. First up is the amplitude. So the amplitude has to do with the height of the graph, and it's actually half the height of the graph. To find that out, we can look at the graph. If we have it, we can see and calculate what half of the height would be. But if I'm looking at the equation, we're going to do the absolute value of A. So remember, height is going to be a positive answer, not a negative answer. So that's why we take the absolute value. So amplitude is half the height of our graph. So you notice our sine and cosine functions, they go up to 1 and down to negative 1. So total, that's a height of 2. But the amplitude is half that height, so the amplitude for both of these would just be 1. Okay, next up is the period. The period is how often the graph repeats itself. So because these were the basic parent functions, these repeated every 2 pi spaces. At 2 pi, we would have started over and it would have followed the same pattern. But not all sine and cosine functions repeat every 2 pi. But we use 2 pi, and we're going to divide 2 pi by b in the equation, and that's going to tell me how often the graph repeats. It's called a cycle, a period, a revolution. Those three words are used interchangeably. So our key, we're always going to start with amplitude and period. I want to see how far up and down does my graph go, and how often does it repeat. Then what we want to look at are there any shifts in the graph? Does it translate left or right, up or down? So a shift left or right is going to be found by taking C divided by B, and that's going to be in the parenthesis with the X. So C divided by B. If that number is negative, then your graph is going to shift to the right that many spaces. If this value is positive, it's going to shift to the left that many spaces. So in parentheses, this direction is always the opposite of what you would think. Okay, then we have our shift up or down, which is D. Now sometimes notice in both of these equations, D is at the very beginning of the equation, but that number could be added or subtracted at the very end as well. So anytime you see a number by itself that's being added or subtracted to the cosine or sine, then that's going to be our shift up or down. This time, this one is the direction that makes sense. So a plus a value would be up that many spaces, and negative would be down that many spaces. Okay, and then last is an x-axis or y-axis reflection. These are the hardest to see when you're just looking at the graph of sine and cosine. Sometimes we can tell that it was shifted in a certain direction or a certain amount, but x and y-axis reflections are difficult because these graphs are so symmetric already to the x and y-axis, it's not as easy to just look at the graph and see. So for an x-axis reflection, we're going to look for a negative a in our equation. And then a y-axis reflection would be a negative b in our equation. Okay, so the goal is going to be to look at these equations and determine how was the basic sine and cosine function changed or translated, and then can we graph those functions? We're going to utilize our calculator to help us as well, but we want to be able to pull out as much information as possible from the equation in order to know how to use our calculator as well. I told you yesterday there's some settings that we're going to have to change each time. Okay, so these equations are not written on your notes, so I'm going to go ahead and add those. For example 1, we have two functions. We're going to look at y equals negative 2 sine theta and y equals 1/2 cosine 2/3 theta. So first thing we're going to want to do is just determine what is the amplitude and period for the function. That's going to help me in a second when I actually start graphing to know some of the settings that I need to change. So let's start with A, which says y equals -2 sine theta. So first thing I'm going to do is I'm going to take this number that's being multiplied times sine. This has to do with the amplitude. So our amplitude is the absolute value of this number. So this is 2. So that means that this graph goes up to 2 and down to -2, or the total height would be 4, but amplitude is always half of the height. Okay, then I want to know the period of the graph, or how often our graph is repeating. So we're always going to start with 2 pi, and we're going to divide by the number that's in front of x, or in this case, theta. So if there was another number in front of theta, we would divide by that number. Right now, there's an understood 1 that is in front of theta. So 2 pi divided by 1 is just 2 pi. That means this graph repeats every 2 pi spaces, or it cycles every 2 pi. Okay, so now we're going to look at B, y equals 1/2 cosine 2/3 theta. So we're going to start with our amplitude. So amplitude is always the absolute value of the number that's being multiplied times sine or cosine. In this case, that's 1/2. So the amplitude is just going to be 1/2. That means this graph would go up to 1/2 and down to -1/2. So the total height would be 1, but the amplitude is 1/2. Okay, now for our period, we're going to take 2 pi and we're going to divide by the number that's being multiplied by x, or in this case, theta. So 2 pi divided by 2/3. So let's remember our fraction rules. When I'm dividing fractions, we're going to take the second fraction, or the bottom one, and we're going to flip it and change to multiplication. So I'm going to do 2 pi times 3/2. We're going to use our brains here. So if I'm multiplying by 2 and dividing by 2, those are going to cancel out. And this simplifies to just 3 pi. So that means that this graph repeats every 3 pi spaces. So in a minute when I label my graph, 3 pi is going to be my very last little mark I'm going to put on the x-axis, and then I'm going to divide up my graph into 4 even spaces. So again, our first job is always going to be figure out your amplitude and period for your functions, because in a minute when we get to the calculator, we're going to use those two things to tell us some settings that we need to change. Okay, now we're going to go to example 2. We're going to look at the relationship between these two functions, and we're going to talk about the transformation that is changed, or what's different between the two functions. So for number 2, I have two functions. F of x equals sine theta, g of x equals sine of theta minus pi. Now technically, since I used thetas over here, I didn't catch myself. These should be thetas on the inside of this parenthesis as well. So anytime you see f or g or a letter outside of a function, that's just the name of the function, so that when I have more than one equation, I know I'm talking about the f function. I can point that one out specifically. Or the g function, I know which one I'm talking about. So instead of just having y equals, we use different names like f or g or whatever letters we want. Okay, so we want to look at the difference between these functions. I know it's a sine function. I know in general what the sine function looks like. I want to see the difference that's happening in these two equations. So what I see is that the second equation is subtracting pi from theta. So if I look at my equation up at the top, this minus pi, I'm going to scroll back up. Minus pi is in the same spot as the c in this equation. So C has to do with the translation left or right, okay? And notice I didn't have another number in place of B. There was just theta minus pi. So that tells me that this is a shift to the right pi spaces. The reason I know it's to the right is because it's a minus pi. So we're going to write that this is a shift right pi spaces. So if I was to graph these two functions, they would look like the same graph. It's just one of them is shifted over pi spaces on the graph to the right. Okay, same thing over here on B. So these should be thetas here. So my f function is cosine 2 theta, and my g function is -3 plus cosine 2 theta. So notice they're both 2 thetas in the equation, so there's no difference there. What the difference is in this equation is this -3 in the g function. So the -3 is in the same spot as the d in the equation up top. The d in that equation tells me that it's a shift up or down. And this is the direction that makes sense. So a minus is going to be a shift down. So we would say this is a shift down 3 spaces. So I would take my whole graph and shift all of the points down 3 spaces. Okay, so we want to be able to compare two different functions and determine how are they different? What's the same? What's different? We could have also figured out the amplitude and period for both of these, but they would have been the same. The only thing that was different was a shift left-right and a shift up-down. All right, so on these next three examples, we're going to be graphing the sine and cosine functions. We might have more than one on the same coordinate plane. On your homework, there's several of them that you're just graphing one at a time. So we're going to look at them one at a time, but we'll end up with two on the same coordinate plane. And then as we're going through this, I'm also going to show you some of the settings you want to make sure you're good on your calculator. So first up, again, is always looking at period and amplitude. So I've got two different functions for number 3. F of x is 2 sine x, and g of x is 4 sine x over 2. So let's start with f of x. So our amplitude is going to be the absolute value of 2. So that tells me that our graph is going to go up to 2 and down to -2. There's no shifting on this one. So I know it's just going to go to 2 and -2. I want to know the period. So I'm going to take 2 pi and we're going to divide by the number that's in front of x or theta. In this case, I put an x. So that would be a 1. So that means our period for this graph is 2 pi. So this one graphs or repeats itself every 2 pi spaces. Okay, and then in a minute, we're going to graph g of x. So again, I want my amplitude and period. So the amplitude this time is going to be the absolute value of 4. So that's just 4. So it's going to go up to 4 and down to -4. My period is 2 pi divided by the number that's attached to x. So in this case, x is being divided by 2, which is the same as multiplying by 1/2. So I need to take 2 pi and divide it by 1/2. So remember 2 pi, and if I'm dividing by a fraction, I'm really multiplying by its reciprocal. So 2 pi times 2 over 1 is going to give me 4 pi. So this graph repeats every 4 pi spaces. Okay, so since I'm going to put both of these on the same coordinate plane, I want to make sure that I'm including all of those numbers for amplitude and period so that I can fit both of them on the coordinate plane. So I've gone ahead and drawn my x and y axis. I know for my x-axis, the biggest period is 4 pi. So I need, however far out I go, I need the biggest amount to be 4 pi. So I'm going to go and mark off every 4 spaces. I could have done 6 spaces or 8 spaces or whatever number I want, but I'm going to go mark those 4 off every 4 spaces. So that means this last mark is 4 pi. Whatever number I determine is the period, then I'm going to divide it up into 4 even spaces. So 4 pi cut in half will be 2 pi. Cut in half again will be 1 pi. And then halfway between 2 pi and 4 pi will be 3 pi. We're going to add some more things in just a second, but this is kind of a starting place for us. Okay, for that biggest graph, the period was 4 pi, the amplitude is 4. So that means I need to make sure to include all the way to 4 and -4. Now these graphs did not shift any direction and there's no reflection, so I don't need any other space beyond these numbers. So I'm actually going to graph the biggest function first, make sure it fits on there, and then we'll come back and modify our graph a little bit so that I can fit the smaller function. So I'm going to use green because I'm graphing the g function first. So since it is the sine function, we know the pattern for sine. It's always going to follow this pattern, and this is why I divided this up into 4 even spaces. Sine, if there's not any shifts, will start at the origin. It's going to go up to the amplitude, back to the axis, down to the bottom, negative amplitude, and back to the axis. So I'm going to follow this same pattern every time I graph a sine function. I'm going to start this way. I'm going to put these 5 points and follow that pattern. Start at the origin, go up, back to the axis, down, back to the axis. Okay? Just the numbers change, but our graph still looks the same. So this is one period of 4 sine of x over 2. We know that this graph continues in both directions. It doesn't stop at those 2 points. Okay, so now I want to modify my graph so that I can fit 2 sine x on here as well. I know that it will fit because the period and the amplitude are smaller. Okay, so for the f function, I know that the period is 2 pi. So I'm going to zoom in here. I know that the very last mark for this one has to be 2 pi. So that means I'm going to fit 2 of these in this amount of space. So I'm going to divide this up again into 4 even spaces. I'm just looking at 2 pi as my stopping point for the f function. So if I divide that up into 4 spaces, now this is pi over 2, and halfway between would be 3 pi over 2. Okay, so I'm just looking between 0 and 2 pi now at these 4 spaces. And sine follows the same pattern. This time, though, the amplitude is 2. So sine is going to start at the origin. At the next mark, it's going to go up to the amplitude, which is 2 in this case, back to the axis, down to the negative amplitude, which is kind of right on top of my 2 there, and back to the axis. So this f function, if I connect these dots, is going to look like this. Now I can continue that pattern in between the 4 pi spaces. It's going to repeat itself again. So I can just kind of copy my points over, and I know that this f function is going to continue in this amount of space, and it's going to look something like this. So normally we're not always graphing 2 functions on the same coordinate plane, but this is just to compare the 2, that changing the period and the amplitude, this is what they look like together. So these next 2 examples, we're just graphing one at a time. So I'm going to kind of use the same rules that I just did. I'm also going to show you on these how we can let our calculator be our friend if we're not sure exactly where our points go. So first thing I need is period and amplitude. So we're going to start with an amplitude is the absolute value of -2. So that's going to be 2. So that means this graph is going to go up to 2 and down to -2. So far we haven't had any shifting or reflections. Okay, my period is going to be 2 pi, in this case, divided by 1/3. So x is being divided by 3, so that's 1/3. So really this is 2 pi times 3 over 1, which is going to be 6 pi. So this graph will repeat every 6 pi spaces. So on my graph, I'm going to decide how many spaces I want to label things. I'm going to just do 4 again so that it's nice and spread out. And I'm going to label the very last one 6 pi. That's how often it repeats. And we're going to divide this up into 4 even spaces. So half of 6 pi is going to be 3 pi. Half of 3 pi is 3 pi over 2. Now here's the tricky one. I need halfway between 3 pi and 6 pi. So think about adding these two numbers together and dividing by 2. We're halfway between them. So if I add 3 pi and 6 pi, that's going to be 9 pi over 2. Okay, so one thing that was different on this function is that number in front of cosine was a negative. So that's going to be an indication to me that there is a reflection. So since that -2, that's going to tell me that's an x-axis reflection. So I didn't label. I need somewhere a +2 and a -2, however many spaces you want. So normally cosine starts up at the amplitude and then we work our way down to the axis and continue the pattern. But since this is an x-axis reflection, instead of starting at +2, I'm going to start at -2. We're going to flip it over. But we're going to follow the same pattern. So I'm going to start at -2. We're going to go back to the axis. This time we're going to go up to +2, back to the axis, and down to -2. We're going to connect our dots. It's easier to go quarter at a time and think about semicircles. We know that this continues infinitely. We're just looking at one period or one cycle of this cosine function. Okay, so let's switch over to the calculator so we can remind ourselves how to change the settings. Okay, first thing, we want to go to mode and make sure that we are in radians because we're graphing in radians right now, not in degrees. We're going to go to window and we're going to make our window match the window on our paper. So some of the ones on your homework, they already have the grid labeled. So you're going to want to use the grid that's on your paper, okay, and make it match this table. So our x minimum is 0. Our x max in this case was 6 pi. X scale is whatever the smallest little tick mark is on your graph. So when we divided that up into 4 spaces, 3 pi over 2 was our smallest little mark on our x-axis. So as soon as you hit enter, it's going to multiply that number out and change it to a decimal. Our y min and y max, we want to make sure to include our amplitude. So I'm going to go a little more than the 2 and -2. I'm going to go -3 and +3 so we can make sure to see things. You can leave the y scale. It's not that big a deal if you adjust that number. Okay, so we're going to hit graph. Oh, we got to put our equation in y equals before we can graph. So we're going to type -2 cosine, and then we're going to type x divided by 3 inside that parenthesis. Now we're going to hit graph. So hopefully the graph on the calculator and the graph on my paper are going to match up. Now we can also use the table to help us plot points if we're not sure about where some points need to go, but we have to adjust the table as well. So we're going to go second window. We're always going to start at 0. We want our change in table to be, again, that smallest little tick mark that's on our x-axis. So that's going to be 3 pi over 2. We're going to go to our table, second graph. So remember, these numbers are going to look weird, but these match up to the 4 numbers that are on my table. So at 0, we plotted -2. 3 pi over 2, that's the 4.7. That was at 0. 3 pi, that's 9 something. That was up to 2. And then continuing so forth. So if you just look at those numbers, you can continue the pattern. When you see numbers like this, 4e to the -13, this is a very small number. This is scientific notation. So this is 4 times 10 to the -13th power. That means that number is very close to 0. So just know, anytime we see that, we're going to either talk about if that number should be 0 or possibly undefined. In this case, it would make sense that that number is 0. Okay, so we can use our calculator to help us. Also, knowing how to set up and label our graph is important with the period and amplitude. Okay, so we've got one more example we're going to look at. And this one has a shift. We've got a couple of shiftings going on. So let's identify the key parts of this graph first before we even put anything on paper. We're going to start with the amplitude and period. So again, amplitude is going to be the absolute value of 2. So in this case, this is 2. So that's half the height of our graph. Period is going to be 2 pi divided by the number it's in front of x. Whatever is being multiplied times x, in this case, is a 1. So that's just going to be 2 pi. So this one repeats every 2 pi spaces. Then we've got two other things happening in this graph. I have a plus pi over 4 in the parenthesis and a minus 1 at the end. So the plus pi over 4 is a shift left or right, and it's the opposite direction than you would think. The plus tells me that it's going to go left pi over 4 spaces, and then the negative 1 tells me that it's going to go down 1 space. Okay, so I'm going to show you how I will start out with the same basic sine function using the period and amplitude, and then we're going to make the adjustments of left pi over 4 and down 1. Okay, we could also use our calculator, but I'm going to start on paper. Okay, so we're going to label our x and y axis. Since my period is 2 pi, I want to make sure however far to the right I go that that is labeled 2 pi. So I'm just going to go every 4 again. So this last one is 2 pi. I divide this up into 4 even spaces. So halfway is pi, 1/4 is pi over 2, and then halfway between is 3 pi over 2. Okay, our amplitude is 2, so we want to make sure, I'm going to just use the actual grid lines here and do 2 and negative 2 since we're going to have some shifting going on. So think about this also. In a second, we're going to have to go left pi over 4 spaces, and I need to be able to figure out what pi over 4 is on my grid. Well, if on my grid I have 4 squares going to the right is pi over 2, then pi over 4 is going to be 2 squares. So that's something, if you're shifting your graph, you want to take into consideration, can I use those squares to help me out? Okay, so I'm going to start in one color, but this is not going to be my final answer. So if you want to use like your pencil very light, or just know that this is not our final answer, we're going to move these points around. But the sine function starts at the origin. It goes up to the amplitude, back to the axis, down to negative 2, back to the axis. This is my basic shape for sine function. Not shifting it. This is just the period and the amplitude. Now we're going to take into consideration the shift that's going to happen. So we need to take these 5 points and we're going to shift each one left pi over 4 and down 1 space. So on my grid, 2 spaces is considered pi over 4. So if I'm going to go left pi over 4, that means I need to take this point at the origin and it's going to go left 2 squares and down 1 square. So this point at the origin is now located here at negative pi over 4 and negative 1. Okay, then I'm going to go to this point up here. We need to go left 2 squares and down 1. This point on the axis, left 2 squares, down 1. Every point is going left 2 squares, down 1, which is left pi over 4 and down 1 space. So now when I connect my dots, oh, I think I messed up somewhere. Maybe I didn't. No, I'm good. We're going to connect my blue dots. The green dots were there just for me to start. When I connect the points, I'm going to use my semicircles and connect the blue dots. Oops, wrong curve. And we know it's going to keep going in both directions. So I could have drawn in my green curve that was the original sine function, and then I shifted everything to the left pi over 4, and down 1 space. Okay, so let's see how our calculator can help us on this problem. So we're going to go type in our equation, 2 sine of x plus pi over 4, close your parenthesis, minus 1. We need to change our window and our table settings. So I'm going to go to my window first. I know that my x max was 2 pi. My x scale is my smallest little tick mark on my graph. I can do pi over 4 or pi over 2, whichever one you prefer. I'm going to do the pi over 2 that was there originally. And then I'm just going to leave my y's going from -3 to +3. That's okay. Okay, I want to change my table settings. So, whoops, forgot. Second window, we always want to start at 0, and we want our change in table to be the same that I made my x scale. So in this case, that was pi over 2. I'm going to go to my table, second graph, and we're going to look at some numbers that are on here and just see how they would make sense on our graph. I'm going to highlight them as we go. So at 0, the ordered pair is 0, 0.4. So notice right here at 0, that's about at 0.4, about halfway there. And then the next mark would be at pi over 2. It's also at about 0.4. These are not the points that we already plotted. We're just looking at about where on the graph. At pi, it's going to be at -2 point something. So notice that point is a little bit below 2. The next mark, same thing. It's a little bit below -2. So we could use those points and still end up with the same curve. I'm trying to help you use the basic shape of the sine graph and the things that we know about shifting the function and period and amplitude. That's how I went from my green dots to my blue dots, but it ends up with the same curve that we have. So if I hit graph, we should see that what's on the graph should kind of match up with our blue graph there.